In the vast expanse of human curiosity, the mystery of why objects fall to the ground has puzzled minds for centuries. Long before modern physics, ancient thinkers sought to explain the unseen force that keeps the world in balance. The quest to understand gravity is not just a story of scientific discovery, it is a tale of human wonder, perseverance, and the gradual unraveling of nature's deepest secrets. The story begins in ancient Greece, where Aristotle, the great philosopher, observed the natural world and proposed that objects moved towards their natural place. According to him, earth and water moved downward, while air and fire moved upward. He believed that the heavier an object was, the faster it would fall. This explanation, rooted more in philosophy than experiment, would dominate thought for nearly 2 millennia, shaping how people understood motion and force. Aristotle's influence was so profound that for generations, his ideas were taken as truth without question. His vision of the universe was orderly, hierarchical, and seemingly self-evident, a world where celestial bodies moved in perfect spheres, unaffected by earthly forces. But while Aristotle's ideas persisted, new thinkers emerged who dared to question them. During the Islamic Golden Age, scholars across the Muslim world sought to refine and challenge classical knowledge. Among them was Al-Biruni, a Persian scientist and mathematician, who carefully studied the Earth's properties. He proposed that the planet might rotate on its own axis and speculated about the force that held objects to the ground. Meanwhile, Ibn Sina, known in the West as Avicenna, pondered motion and inertia. Unlike Aristotle, he suggested that an object in motion would stay in motion unless an external force acted upon it. Though his ideas would not be fully understood until centuries later, they marked a significant departure from the old ways of thinking. As the medieval period unfolded, European thinkers began to re-examine nature through the lens of reason and observation. In the 14th century, Jean Buridan, a French philosopher, introduced the concept of impetus. He proposed that objects in motion carried an internal property that kept them moving until another force intervened. This idea was a critical step toward the modern concept of inertia, though it lacked the mathematical precision that later scientists would bring to the table. Buridan's work influenced later medieval scholars, who slowly edged closer to breaking away from Aristotelian thought. Then came the Renaissance, an age of renewed curiosity and scientific exploration. Among the many minds that flourished during this time, none was as influential in the study of motion as Galileo Galilei. The 16th century Italian scientist, armed with a keen mind and a willingness to challenge dogma, performed a series of bold experiments. To test Aristotle's assertion that heavier objects fell faster than lighter ones, he is said to have dropped spheres of different masses from the Leaning Tower of Pisa. The result was shocking: all objects, regardless of weight, fell at the same rate in the absence of air resistance. Galileo's studies did not stop there. By rolling balls down inclined planes, he demonstrated that an object in motion would remain in motion unless a force acted upon it. He formulated the principle of inertia, laying the groundwork for what would later become Newton's first law of motion. His meticulous observations of the heavens, aided by his improvements to the telescope, further eroded the Aristotelian view of a perfect, unchanging cosmos. The stars and planets, it seemed, obeyed the same laws of motion as objects on Earth. The 17th century ushered in a true revolution in the understanding of gravity. In England, a young mathematician named Isaac Newton would take the puzzle of motion and force to new heights. The story goes that while sitting under an apple tree, Newton saw an apple fall to the ground and asked himself, could the same force pulling the apple downward also govern the motion of the moon and planets? This simple question led him to formulate his universal law of gravitation. Newton's insight was profound: every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. His magnum opus, Mathematical Principles of Natural Philosophy, published in 1687, became one of the most important scientific works in history. Newton's equations allowed scientists to predict the orbits of planets, explain the motion of comets, and even understand the tides. His laws remained unchallenged for centuries, providing a framework for everything from engineering marvels to space travel. But the march of discovery did not end with Newton. As the 19th century dawned, new phenomena hinted that Newton's theory, though powerful, was not the full story. The orbit of Mercury, for example, did not match Newtonian predictions, leaving scientists puzzled. For decades, researchers searched for an explanation, some even hypothesizing the existence of an undiscovered planet near the Sun. The true answer would come from a mind unlike any other. In the early 20th century, Albert Einstein introduced his groundbreaking theory of general relativity, which redefined gravity itself. According to Einstein, gravity was not merely a force between masses, as Newton had proposed, but a consequence of the warping of spacetime caused by massive objects. A planet orbits a star not because it is pulled by an invisible force, but because the star's mass bends the fabric of spacetime, creating a natural path for the planet to follow. Einstein's theory was not just an elegant idea, it was confirmed through observation. In 1919, during a solar eclipse, astronomers observed light bending around the Sun exactly as Einstein predicted. His ideas would go on to explain black holes, the expansion of the universe, and even time dilation near massive objects. Gravity was no longer a simple attraction between bodies, it was a fundamental interaction shaping the very structure of the cosmos. The journey of understanding gravity has been long and winding, shaped by brilliant minds and daring ideas. From Aristotle's natural tendencies to Newton's equations and Einstein's warping of spacetime, the story of gravity is a testament to human ingenuity. Even today, physicists search for a deeper, quantum theory of gravity, hoping to bridge the gap between Einstein's relativity and the strange world of subatomic particles. The quest continues, but the force that binds the cosmos remains one of the greatest mysteries and triumphs of science.